Yeah, so this week we will try to finish off the topic about the waves, right? And then next week we will start to talk about relativity already. So that will be a more difficult topic. But yeah, so we will need to finish off waves first. So let us discuss two more remaining topics. If we don't have time, we will probably continue the last topic on Doppler effect on Wednesday, right? And also don't forget, let me remind everyone before I also forget that we have another quiz this week, right? So quiz 3, our final quiz of the semester, and then in 2 weeks time, the last day of week 15, the assignment is due. Okay, so just keep those things in mind. Let us get started about the another phenomena related to waves is the coherent interference and double slit, right? So one of the defining features of wave is the superposition principle. We discussed this last week. Two waves can interfere with each other, and it depends on the wave, right? So if the two waves having the same phase, the result will add up a larger amplitude or a larger displacement. But if the two waves having opposite phase, they will cancel each other, right? And we see this phenomena in the Young's double slit experiment. So in this experiment, we take light as waves, and then we shine a light through two empty holes, and then we shine it on the screen. And then we try to calculate what we expect to see on the screen, and we see, and it will agree with the experiment. So this phenomena is related to the waves. Okay, so let us consider this problem now. Okay, so as usual, we will be solving a system related to a sinusoidal wave. So a sinusoidal wave is usually written in this form, right? And then I got the kx minus omega t, where my k is 2 pi over lambda. Remember, lambda is a wavelength. Omega is angular frequency, so it's 2 pi f. F is just the frequency of the wave, and then f times lambda, if you multiply them together, you get the speed of the wave, right? So, and an important thing when we discuss about the interference is we need to know what is the phase of the wave. So if a wave is given in this form, the phase, right, let me remind you, is I call this symbol phi, and then this is kx minus omega t. So whatever is inside the sine function is the phase. So this is my phase over here. Okay, and then now we want to consider the interference between two waves, right? Because double slit is the double slit experiment is about light shining through two holes and then shining onto the screen, right? So this is interference of two waves. So we will consider two waves, basically two light sources, right? So two light sources shining on a spot. So I have two waves, right? And then we will let our origin be the source of the wave. So it's generated by a source at x equals to 0. So if I draw the wave, it's going to look like this, right? And wave 1 is going to look like this. And remember, right, because this is depends on x and t. So for different t, I will get different shape of the graph. So every time I draw something, I draw a wave, it's only for a moment in time of specific t. So for the propagating sinusoidal wave, right? So let's say my source is here at x equals to 0. This is my x-axis, right? So maybe my wave is until here, right? So let's say the light source is here, and then I shine onto something, a screen or some surface here. The position is L1 distance away from the source. So the distance from the source to this point is L1. Okay, so this is the distance. And then if this is the situation, right, then what is my phase at this position? So the phase at this position, so this is, let's say I'm drawing this at some time equals to 0, right? Or some time, any time, right? So a moment in time, right? So the phase at position x equals to L1 is for wave 1, I just substitute x equals to L1. So I got KL1 minus omega t, right? So at some moment in time, at some particular time, this instant is like this, okay? Now let's look at what happens to a second wave. So I have wave 2, right? So I wave 2, and then I let the origin be the source again as well. So at x equals to 0, this is the source of the wave, right? And then I got this, right? And then let's say I stop until here, right? So this is position L2. So the distance of this is L2, okay? Or maybe I'll do it this way. So yeah, so I let this be L2, right? So so if when I draw it this way, it's going to be destructive interference. When I draw it this way, it's going to be constructive. You know what I mean, right? But in any case, right? So the phase at position x equals to L2 for wave 2 is phi 2 is equals to KL2 minus omega t, right? So I got the two waves and I calculated the phase at some position later, right? So hopefully everyone can follow, because I'm not doing anything complicated here. I just substitute the position for each wave, right? So I got two waves, and then the assumption is I draw in such a way that I start from 0 here. So that means waves 1 and 2 have the same initial phase, which is that the phase is 0 at position 0 and time 0, okay? Oh yeah, I forgot to write the equation for the wave. So the wave 1, the equation for wave 1 is A sine kx minus omega t. And then the wave 2 is also the same. So y2 is equals to A sine kx minus omega t, right? So this is my two waves. So what if I interfere these two waves? So before I interfere, right, same thing as I shown you last time, I need to know what is the phase difference. So the result of the interference, at the end of the day, it just depends on the phase difference. So I want to calculate the phase difference. Phase difference between wave 1 and 2 is what? So the phase difference, I will call this delta phi, and this is phi 2 minus phi 1. Okay, so phi 2 is this expression, phi 1 is this expression. So just subtract these two, omega t minus KL1 minus omega t, right? So notice that the time in this case doesn't matter, because omega t, they cancel each other, right? They minus. And then KL2, KL1. So this is equals to KL2 minus L1. So my phase difference is equals to KL2 minus L1, right? So we're going to keep this in mind for later, right? So yeah, is there any question? Am I recording? Test. Okay, so yeah, so this is the situation that we have so far, right? So I know I have calculated this position given at this distance. This is this, and then this is this. So now what I'm going to do is I'm going to interfere these two waves. So that means let's say this is the two light sources, right? So I shine these two light sources on the same place, and let's see what happens. So we let, okay, so we let how to say, we let waves 1 and 2 interfere at point P. Okay, so let's say I have, this is my wave 1 source, right, shining a light, right, and then I shine at point P. So I shine on point P. Okay, then I have another wave, so I got a wave 2 source. Okay, and then I shine the light, so I shine it until point P. Okay, and then I see what is the result of this interference. So the distance from here to here is L1. The distance from here to here is L2. So because I can shine it in any way, right? I do not expect L1 and L2 to be the same, right? They could be different. So let us calculate the interference. And by the superposition principle, right? If y1 and y2, they are solutions to the wave equation, because definitely they are just the sine function, right? And we have spent a lot of time showing that it's a solution. So y1 plus y2 is also a solution. So y1 plus y2 is also a solution. Okay, and what is y1 plus y2? So y1 is a at point P, right? So we're going to calculate this specifically at point P. So at point P, right, my function is equals to a sine of y1. So y1 is a sine of the phase. The phase is KL1 minus omega t. And then for y2, the phase is just KL2 minus omega t. Okay, and then what is this plus this? So we are going to, let me remind you of the trigo formula again, right? If I have a sine of an angle plus a sine of another angle, this is going to be equal to 2 sine of angle plus angle over 2, and then cosine angle minus the second angle over 2. Okay, so if I use this identity, then this is going to be what? 2a, and then cosine of the difference. So let me take the cos of the difference, this minus this, right? So I got KL2 minus omega t minus KL1 plus omega t over 2, and then sine of the sum of these two angles. So KL2 minus omega t plus KL1 minus omega t over 2. So on this case, this part is the phase difference over 2, because we see that this is y2a cosine k factorized, so I got L2 minus L1 over 2, and then on this term is a sine function, and then a sine function of KL1 plus KL2 over 2 minus omega t over 2 is just omega t again, right? So yeah, so this part, as you can recognize, is actually the phase difference over 2, and this is sine of some function over omega t, right? And this is a coefficient because I'm calculating at a fixed point P. So at fixed point P, right, it is some number L2 and some number L1, because it's determined by this diagram, and I have some sine of some fixed number minus omega t. So do you remember what is this equation? This is a simple harmonic oscillation, right, at point P. Okay, so at point P, what we have here is that this is a simple harmonic oscillation. At point P, right? So at point P, so the wave is simple harmonic oscillation, and then with the frequency is still omega, right? Just that there's a negative omega. And amplitude, what is the amplitude? So the amplitude is whatever that is in front of the sine function. So all this is a number. So the amplitude is 2a cos of KL2 minus L1 over 2, right? So it's actually the phase difference, right? So it's, in other words, 2a cosine of phase difference over 2. Okay, so this is a simple harmonic oscillation with a new amplitude. And what is this amplitude? So the amplitude depends on the phase difference. So I can find a situation where it is possible that the amplitude can be 0, right, if I choose a correct angle inside here, or the amplitude can be the largest possible value. So largest possible value is when cosine is 1, then I get this. So these are the two cases that we will study in detail. Okay, so does anyone have any question? How to manipulate any wave? Actually, it's quite easy. It's quite easy to manipulate light wave. Yeah. So if you just buy a laser pointer, right? You can actually do this experiment if you have a laser pointer. Yeah. So how to manipulate any wave, right? If I'm talking about light wave, is the easiest is actually the light wave. So just use a laser pointer. Yeah. I actually if there's no MCO or no lockdown here, right, I have a laser pointer in my office, then I can actually show you. But right now, I can't go to the office, so I can't get the laser pointer there. But yeah, you know what I mean, right? The laser pointer, yeah, you just shine it through something, right? And then you can see it in the interference to happen. Okay, so that is one way to manipulate. It can also happen for manipulation of the wave shape of the laser. So the wave shape of the laser is yeah, for any wave, right, the important information you need is the wavelength and the frequency. So normal laser pointer, right, the wavelength is about 650 millimeters. The red color light laser, so it's about 650 millimeters. And then frequency you can calculate from the speed of light, because if you're talking about laser, right, laser is light, so the speed of light is c. So using the speed of light dividing by the wavelength, you can calculate the frequency. And then the wave shape will be the shape for one instant in time is frozen like this, but for different moment is at different configurations. Okay. Yes. So the wavelength of the laser depends on the color, or the color actually determines the wavelength. When we see color with our eyes, right? So when we see, like, how come we see something as blue color or red color? It's because our eye is measuring the wavelength of the incoming light. So the color is correlated to the light. Okay. Yeah. So so what we have so far now is if I shine something at some point P, right, then the resulting wave is this one you will learn in the next course, the electromagnetism. The wave is actually the electric and magnetic field oscillating. So at point P is oscillating, and then the amplitude of the oscillation depends on this. Okay, so what we want to do now is let us explore the two special cases. The firstly is I want to consider about the constructive interference. So for constructive interference, right, I want to study the case that for light, so yeah, remember, right, when we're talking about for light, very bright means large amplitude. Okay, sorry, here. For light, large amplitude of the oscillation, and then dark means low amplitude or zero amplitude. Okay, so the amplitude of the wave is the brightness. So I want to find a case where the interference will give you a very bright effect. So that is the constructive interference. So point P, the oscillation at point P has the largest amplitude. If the amplitude, how do you make this amplitude to be as large as possible? So I want this amplitude to be large as possible. If these are fixed numbers, so cosine, right, can be from -1 to 0 to +1. But if it's either -1 or +1, that will be the largest amplitude. So cos amplitude delta phi over 2 is equals to +1 or -1, also fine, right? So in other words, what is my amplitude? My amplitude is k L2, my phase L1 L2 over 2. How do you make a cosine to be +1? That means this thing, right, must be equals to an integer times pi. Okay, so that is what you get. Color of lightning. You mean like the thunderstorm lightning? Yeah, that's interesting to think about. Yeah, I'm going to think about this later. Yeah, so I will talk about this later when we talk about the experimental part, right? You can do it using the same light source. Yeah, lightning thunderstorm, let's see. So lightning, that's a complicated process, right? That one is really about electromagnetism. So the lightning thunderstorm happens when there's a very strong potential difference. The friction between the clouds will cause a potential difference, and then it causes the electric breakdown. So the electric breakdown means the electron flow through the atmosphere, and the flow of electron atmosphere collides with the air molecules. So the air molecules will get excited, and then it will relax again, and the energy levels between that will determine that color of that lightning. I assume. I imagine. Yeah. So it's more of a quantum process that determines the color of that lightning, right? So that one is like the next semester topics. So right now, right, we haven't even considered all that. Right now, we just say that, oh, given a light, let's say we already have the light and we already know the color, right? So we don't know what causes the color yet, right? That is the complicated process I was talking about earlier. With laser, it's different story. With lightning, it's a different story. With a light bulb, it's also a different story. Now, light bulb is what you probably learn in thermodynamics, the Planck distribution, right? The Rayleigh-Jeans distribution. That the color of the object depends on the temperature. If the light source is a thermal source, right? So it's a lot of complicated, not complicated. Different light source is caused by different phenomena. Not complicated, it's just different phenomena, right? Thermodynamics, electromagnetism, or quantum mechanics, right? So all these phenomena can cause light. So which is a lot of interesting things that you will learn more later, right? So right now we're only starting the first few topics. But for now, right, yeah, we have the largest amplitude in my cosine function is equals to this, right? So this is my phase, right? So let us write the integer as n pi, right? So I'm gonna write this. Normally we write integer as n pi, and then this k, right, is 2 pi over lambda. Remember, k is 2 pi over lambda, right? And then I got L2 minus this L1 over 2. Okay, so we realize that the 2 will cancel here, and then the pi will cancel here, right? And we conclude that L2 minus L1 is equals to integer times lambda. So I have found a condition where the two light sources will cause a constructive interference. If the distance traveled between L1 and L2, right? So if the length difference is exactly integer times pi, this is constructive interference, right? So I get the bright spot at P, right? So this is constructive interference. In other words, usually I call this the path difference, because we notice that the total length of the individual light is not so important, but the difference between the two lengths is important. So the path difference must be integer times the wavelength of the light. Okay, so this is a condition for constructive interference. Okay, yeah, so let me highlight this because this is our main result. Okay, so this is our constructive interference, and what happens is, well, I have light 1, right? So it depends on not the individual distance, but the difference. So let's say the difference is like this, right? So this is L1 over here. So if I want to have constructive interference, I have this one and then maybe this one. Okay, so this will give me constructive interference. Why? Because let's say this is L2, right? This is L1. Okay, so the difference, what is the length of this? This is like one cycle, right? So this is one wavelength. So in this case, this is one wavelength, n lambda, where in this case n is equals to 1. And of course you can do n equals to 2 also, or n equals to 3, or n equals to 4, right? So as long as it's the multiple of a wavelength, the extra distance traveled by the other wave, right? The extra distance by the other wave, as long as it is a multiple of the wavelength, the reason why I want multiple of the wavelength, so I got the same phase. So this is the peak, right? So the upwards and then plus the peak. So in the two same situation, when you add them together, you get an even larger amplitude. So that is why we get the constructive interference. Okay, so any questions so far? Okay, so everyone follow? Okay, so if you follow constructive interference, then destructive interference is the same, right? It's just the opposite situation. So let us study destructive interference, right? So destructive interference. Okay, so destructive interference, I have point P has 0 amplitude, because I want destructive interference means I want to shine the light on point P, right? And then destructive means the two light cancel each other out. So when the two light cancel each other out, they disappear. So you see darkness over there. So I want to have 0 amplitude. So I have 0 amplitude when, well, my cosine, right? So remember my amplitude formula. It depends on this cosine function. So if my cosine function is 0, then I will get 0 amplitude. Okay, so how do I make cosine function 0? So to make this cosine function 0, right, delta phi over 2 must be an odd number divided by 2 times pi, right? Cosine 90 degrees, right, or 3 pi over 2, 5 pi over 2, cosine of all those numbers, they will become 0, right? You can check with your calculator. Okay, so remember that delta phi is the k times the path difference, so k L2 minus L1 over 2. And then how do I write down an odd number? Well, if I take an integer times 2, right, I guarantee to be even number. Then if I minus 1, I will make it an odd number, so pi, right? So m is an integer. Okay, so integer can be 0, plus 1, negative 1, plus 2, negative 2, any of those numbers, right? Integer. So these are integers, and then I realized that I can actually cancel the 2, and then my k is, remember, is 2 pi over lambda, so L2 minus L1 is equals to odd number over pi, and then I can also cancel the pi, so L2 minus L1 is equals to, divide the 2 down, I will get m minus half, and then lambda. Okay, so the m is an integer, and then if I minus half, right, I will get some integer, another integer divided by 2. So what I got here is that the condition for destructive interference, right, so I got a dark spot at P, and to get this, the path difference of the two light is, well, integer minus half, I will get something called a half integer, because it's something divided by 2, right? So half integer times the wavelength. Okay, so this is our second condition, which corresponds to destructive interference. Okay, so condition for destructive interference. Okay, so how does it look like? So half integer means, right, so let's say I got my wave 1. Okay, so wave 1 is maybe here, right? So let's say the distance traveled is L1, and then I got second wave. Okay, so something like this. Okay, and then I continue on. Yeah, so let's stop here. If I draw longer, I will start to confuse myself. L2, right? So what is the difference between L1 and L2? So in this case, right, the difference is half a wavelength, right? So this is half a wavelength. So that means I'm considering the case where m is equals to 1, right? So for if it's a half a wavelength, this is the situation where I get the destructive interference, because over here I got a peak, over here I got a bottom. So if I take these two waves and interfere, right, the peak and bottom, they will cancel each other out. Then this is how you get 0. Okay, So this is the destructive interference. Am I recording? Yes. Light bulb. No. So that's the thing. For light bulb, right? Light bulb, the light coming from a light bulb has a range of frequencies, and it does not satisfy our condition. So you can't. Using light bulb, you can't. Yeah. Why? Because this is also kind of important thing. What was our initial assumption that make all this calculation possible? That I started with two waves with the same equation. That means, right, our assumption is wave 1 and 2 have the same initial phase. Okay, so same initial phase. So same initial phase, another word is coherent light. Okay, so for light bulb, right, actually the light, even for different parts of the light bulb, they are already not in the same phase. Then the second bulb, totally not in the same phase. So they cannot cancel each other perfectly. That's why for these experiments, you need the laser. Yeah, light bulb is white, so it's a mixture of different frequencies. Yeah, that is also another reason. Correct, yes. Single color, so yeah. Yeah, so we also need another important condition is we need the light 1 and light 2 to have the same frequency. Everybody have the same frequency, therefore same wavelength, so that for this distance exactly you got this. But if I have the light correspond to different wavelength, right, then you can only cancel one color, but other colors cannot cancel already, right? Or constructive also. For one color it can be bright, but for another color it's different. So this is also another thing to consider. How to make sure the initial state is the initial phase the same? That is the experimental problem. So I'm not very good at it, but laser. Okay, so laser. For laser, right, all the light coming out of a laser is the same phase. Yeah. So yeah. So I guess these are some interesting facts. So let me write this down. Right. So so let's say coherence of different light sources. Okay, so for example, right, laser. So laser, all light is the same phase. All parts of the light, I should say, are actually if you go more advanced theory of laser engineering, right, actually it's not perfectly the same phase, but like majority of the light is the same phase, are, so I should say mostly the same phase. But in the ideal case, we assume it's same phase. Right, so let's say I have a laser. Okay, so some laser machine. Okay, and then yeah, so every part of the light will come out at the same phase. So everything is nice. My drawing is very ugly, but same phase lah. Okay, if I have light bulb, right, light bulb, this is due to this is a thermal phenomena. And you guys have learned in thermodynamics, thermal phenomena is random and depends on probability and statistics. So it's very hard to make it same phase, so not coherent. Right, not same phase. Right, so I have a light bulb. How to draw a light bulb? Right. Right. So the light bulb will be, in fact, it's a mixture of different colors. So it's all random and all mixed up together. Right, so it's a very messy thing, right? And it goes out in all directions. So it's even more like it's a total mess. So you cannot do interference experiments with light bulbs. It's very difficult. You can choose a filter and polarizer to filter out the correct phases. That is also like yeah, you need a lot of effort to make turn a light bulb light source into a coherent light. right? So this is what in optics, right? In electromagnetism later is about the coherence. How do you make light coherent? So this is like a totally different set of topics that is quite challenging and a lot of things to consider, right? So right now we are assuming laser, where all the light source are mostly in the same initial phase. Lightsaber, yeah. So lightsaber can be cancelled by, interesting. Is lightsaber supposed to be light, or is just a solid that that is very bright? That is also another thing. Yeah. White color laser, that is, yeah. Is it possible to even have white color laser? Right, white by definition is a mixture of mixture of different things. And then there's also a dark saber, right? It's a black color source. Yeah, so it comes from a Jedi crystal and things, and then I imagine lightsaber is more like the plasma cutter, right? It uses heat, like a fire, like the in construction people they use the heat to cut the metal, right? That to me feels how a lightsaber works more in real life than light, because light, right? Superposition principle. If you have two light passing through each other, superposition, we learn this phenomena, they just pass through each other, so you cannot fight each other like a sword fighting, right? So it must not be a wavelength composed of light. Yeah, it won't collide. Okay, I will check this out later, but for now let's talk about the Young double slit experiment. So this one can answer your question, how do you make sure wave 1 and wave 2 are the same light? Because I have a laser that all parts are coherent, right? So I have some laser light source, right? So I have a laser light source, right? And then I shine through a object with a gap. I think it's too ugly. Wait, let me draw nicely. Okay, so let me draw this. Okay, so this is two holes, S1 and S2. So I shine a light, S1 and S2, and then I will create a source of two coherent light sources. Okay, so the distance between these two is, I will call this D, right? So I shine it through two slits, right? So two slits, that's why I call it a double slit experiment. Two slit means there's something with two holes. So I shine a light with something with two holes on it, so I got two holes of light sources coming out, right? So and then I shine this on the screen. Okay, so shine this on the screen, and then the screen will be my y-axis. Okay, so this is my x-axis, so this is my y-axis, right? This is my screen. Okay, so if I have a light shining on, let's say at my point P, right? So my point P is at y equals to some number, so some height from the axis. So this middle point, right? This midpoint horizontal line that is perpendicular to the screen is usually what people call the optical axis. Okay, and then I have the light shining from here to here, and then the light shining from here to here. Okay, so I want to find out what is my double slit experiment. What is the what you see on the double slit experiment? Okay, so this is the setup of our experiment. Oh, is it? Okay, I will watch it in break time. But now we have to solve this first. Okay, so the distance between the two slits is, we call this D, right? And then the distance from the slits to the screen is called R. Okay, so I have some experiment, I have some laser, right, and then I shine it through something with two holes, then I shine the light, and then I shine it on the screen here, and then I want to see what happens on the screen. Okay, so let us try to calculate this. Again, right, in order to make the calculation, because the math is going to be very complicated, so we need to simplify our assumptions. So we're going to make another assumption. We're going to assume, okay, we're going to assume that the R is very far away from the screen. So the screen size is some screen here, and then the light source is something very far away. So R is a very large number. Okay, then if I do this assumption, right, if I assume this is very far away, then the lines S1 to P and the second line S2 to P are approximately parallel. Okay, and if both approximately parallel, both approximately at angle theta with the horizontal axis, which is sometimes people call this the optical axis. Okay, so what do I mean when I do it this way? So that means, right, if I zoom in, so if I zoom in on this part, right, S1 and S2 are here. Okay, so this is source 1, this is source 2. Okay, so the two lights, if these two are very, very far away, right, then these two lines, the further away, the more approximately is like a parallel lines. So it's like parallel line and parallel line. Okay, so this is the horizontal direction. So the horizontal direction is with angle theta. And then if I make this assumption, right, now I can calculate the condition for interference. Remember what is the condition for interference. Let's start with constructive interference. To have constructive interference, right, the difference in the distance traveled must be integer times lambda. So if I want to have, I need to calculate what is the path difference, right? So the path difference so this is light 1, this is light 2. Is what? What is the path difference? So if these two are parallel, right, that means I can approximate that this part is the extra distance traveled by light number 2. Okay, and then the rest should be the same until point P. We assume approximately the important path difference is this distance here. Okay, so if this angle is D, right, and then this angle is theta, so the path difference is D sine theta. Okay, so this is D sine theta. Okay, so D sine theta, and because R is much larger than Y, right, then another result is if R is a very large number, theta is also a very small number, right? So what I'm trying to say is this one is also small, a small angle. If this is a small angle, then D sine theta is approximately equals to D tangent theta, and it is approximately equals to Y over R. Okay, so as long as this is what we call the far field approximation. If the screen is like very far away, right, actually far away means 1 meter, 2 meter, because your light source is your laser pointer. So your laser pointer is just some small thing over here, and then your light source is like 1 meter or 2 meters away. You can already use this equation. Okay, so 1 meter or 2 meter, sine of some angle, right? Your screen is also some small size, something like this, right? What you see is some piece of paper here, and then 1 meter away, the angle is going to be very small. Okay, so this equation is going to be valid. So then I can now calculate my condition for constructive interference. So if I want to have constructive interference, so in order to have constructive interference, my path difference must be n integer times lambda, and this is my path difference. So d sine theta must be integer lambda, right? So n is an integer. Okay, and also sine theta I can approximate to be y over r, so dy over r is equal to n lambda. So I can finally calculate the position for constructive interference, which is just n lambda r over d, right? So n is an integer. Okay, so what does it mean over here? So that means, right, for a different integer, I can calculate the position of the bright spot. So let me just draw the screen, right? So let's say this is y equals to 0, right? So 0 is one of the integers, so at the middle I will get the bright spot, right? And then if n equals to 1, lambda r over d, so this is lambda r over d is another bright spot, and then 2 lambda r over d is another bright spot, and many ones over there. So negative integer is also an integer, so negative lambda r over d is another bright spot. This is negative 2 lambda r over d is another bright spot, and so on and so forth. Okay, so this is the case where n equals to 0, this is n equals to 1, this is n equals to 2, this is n equals to negative 1, n equals to negative 2, and so on and so forth in both directions, right? So these are the locations where you get the bright fringes. We call it the bright fringes. Okay, so this is how you get yeah, so let me Google the Young double slit to show you how it looks like. Okay, let me make sure it shows on the screen as well. Okay, so let's see some pictures of the double slit experiment. Okay, yeah, so what you have here, right, the experiment is like this. So this one using electrons, so I don't want to touch electrons yet. Yeah. But I think you can see from here already, right? So what you see on the screen is bright, dark, bright, dark, bright, dark. So the dark part is the destructive interference. The bright part is the constructive interference, and I have some light source shining onto. So this is a second way to create a coherent light source. You have S1, S2, right? So this one is not using laser, but some other thing. But the same point holds. I have two light source shining onto a screen. So I got the bright, dark alternating sequence over here. Okay. When electron behaves as a wave, the word GG. Well, the electron do behave like a wave quite often, and this is also another thing you guys will learn in modern physics, which is the next course you will take in the April, Sam? Yeah, next April. You will learn this. The electron, right, behaves like a particle, behaves like a wave. Then you get the wave particle duality. Yeah, all those things. You will study that in the next course. Why? You mean sad or tears? This is the tears crying emoji, is it? Oh. I mean, it's the same for everyone. Students who learn quantum mechanics for the first time is actually, I think math will be more of an will be good, comfortable for math, because yeah, the concept sounds very strange at first, right? But at the end of the day, quantum mechanics is just calculating the probability distribution. So once you like stop focusing too much on the weird like electron things like that, and then you get the probability distribution, it's just statistics, right? It's just calculating the probability distribution. So in that sense, quantum mechanics can become easy, right? But of course, it's challenging topic for students who learn this for the first time. Right? But let me finish off this thing before I start rambling about other things. Let's talk about the destructive interference. So I want to find the position on the screen where on the screen that is the dark spots, right? You've seen the picture already. So the destructive interference, I want to have the dark. So to have the destructive interference, the path difference is d sine theta must be half integer. So m minus half of the wavelength, right? So m is an integer, right? And d sine theta is approximately equals to y over r, and this is m minus half lambda. So the coordinates for y is m minus half lambda r over d. So this is the formula for the destructive interference, right? So yeah, then for these positions, you will get the dark spots over here. Yeah, so actually in my lecture notes, I got a better looking experiment over here. Yeah, so if you use, usually the laser that we use right in the school laboratory is the 650 laser, the red color laser, right? So if you shine this and take a picture, you'll probably see something like this, right? Very red, then dark, red, dark, bright, dark, bright. Okay. Yeah, any question? Oops, did I turn off the, yeah, I turned off the Firefox. Yeah, so math major, will you take quantum mechanics? Yes, math major will be allowed to take, yeah, as a major elective. Modern physics also got correct. So if you if the math major, right, if you are interested in like the actual quantum mechanics with where all your math skill can come into play, right, because that is the year 2 quantum mechanics. Yeah, so what we have so right now, right, our physics majors right now, you guys are in year 1 sem 1, right? So right now you are taking mechanics, and then thermodynamics, right? And then the math course are the linear algebra, calculus, and then Python, right? And then year 2 sem 2 is going to take electromagnetism and modern physics. So modern physics is not really quantum mechanics yet. It's just like the beginning quantum mechanics for beginners. Okay, so that is like the simple quantum mechanics, and it's only a few chapters because modern physics cover other things as well, atomic physics and things like that. Year 1 sem 2, right? So and then there's a short sem, and then there is for physics majors year 2 sem 1. I think you will take the classical mechanics, and then quantum mechanics, the higher level things. So this one is probably where, you know, where all the things like the Schrodinger equation comes in, right? So you see equations like this, and for, I believe, you know, math people will be more interested in this part because this is where you use like the linear algebra, complex analysis, all the function spaces, all the orthogonality of functions will come into use on this part. Okay, yeah, so in any case, right, yeah, so I think now we can take a break now, since we are not we finished the interference stuff already. So yeah, so let me stop the recording and then we shall take a 10 minutes break. Then suddenly in the second movie it's like, wow, so touching. Okay, so let's talk about the tutorial now. Yeah, so I guess we started doing tutorial on Mondays because we have the quiz on Wednesday, so it will make more sense to do tutorial questions before the quiz. But I already uploaded the solutions, so I'll just do some of them. Then, as usual, for those part you don't understand, you can ask me later at some other time. Okay, so let's just do some questions and then let's see how we go. Right, so let's do question 1. Question 1 is the basic. So given a transverse wave, you have the amplitude, you have the k, you have the omega, and then determine all these quantities. Okay, so it's very basic. So let's just do this as a warm-up. Right, so I have a wave that is given by a sine kx minus omega t. Right, and then the amplitude is 6.50 millimeters. The wave number, we call it the wave number, is 2 pi over 28 radians per second, per cm, sorry, because the wave number is measuring length, and then the angular frequency is something to do with time. It is 2 pi over 0.036 radians per second. Okay, so what we want to do is to determine the amplitude. Amplitude, nothing to do, is just A itself. Right, so to know this answer, you just need to know A means the amplitude, so it's 6.5 millimeters. Okay, the second thing that you want to figure out is the wavelength. So the wavelength we can calculate using the wave number, so it's 2 pi over k, so it's just 2 pi over k itself is 2 pi over 28. Right, so it's just this is in cm, so the answer is 28 cm. And then I want to know the frequency. So the frequency can be calculated from angular frequency by omega divided by 2 pi. Right? So omega itself is 2 pi over 0.036 and then divide by 2 pi. So this will cancel the 2 pi. And this gives me 27.8 hertz. And then the d is the speed of the wave. So the speed of the wave is v is, I can calculate using omega k or using f lambda. Either way is fine because they are the same equation. They're cancelling the 2 pi each other. Right, so omega is just 2 pi over 0.036 and then k is 28 and then divide this two, I got 777 centimeters per second. Okay, so these are some basic things, some basic features about the wave. Okay, so yeah. Chapter 8 and 9, I got say in the announcement. So is what we discussed last week. So yeah, if you did not get the email, it's over here on the Moodle. Why so slow? Okay. Yeah, sorry, it's kind of slow. Um, 9.4, yeah, I will try to remember 9.4 is the standing wave things. Okay, so chapter 8 to 9.4. Okay. The final is everything. Yeah. Everything after the midterm. But of course, right, everything after the midterm still need to use Newton's law. You still need to draw free body diagrams, right? Yeah, so those are basic things. So you can't say it's not including the front part also, right? Final boss. Yeah. Final boss is, of course, should be the most challenging, right? And the quiz are the mini bosses. So let's do question 3 now. So question 3 is about this. So question 3 is some physical configuration. I have a steel wire, right? Is attached to the ceiling, and the other end is hanging a 54 kg object. So it takes a transverse pulse this much time to travel from bottom to the top, right? So this time divided by this distance will give you the speed of the wave. So from here, can we calculate the mass of the wire? Okay, so let's do this. right? So the length of the steel wire is 3.80 meters. The mass of the hanging object is 54 kg. So what's going to happen here? That means, right, what I have here is I have a ceiling, right? I have a steel wire hanging onto this, right? So from here I can solve the free body diagram. See, even though final I didn't say everything after the midterm, you still need to draw free body diagram, right? So it cannot be escaped. So the tension of the string is what we call F0 in this wave equation notation, right? So in equilibrium position, right, if it's balanced, then the tension of the spring is equals to mg, right? So from here we got mg, the tension of the force, tension of the string is equals to the weight. Okay, so this is the system that you have now. Then if I sort of plug the string or slightly disturb the string, it will do some small vibration, right? It will do some small vibration, and this vibration is the wave propagating on the string. So you have the formula that is the speed of the wave propagating is equal to the tension over the mass per length, right? So what I want to do is I want to calculate the mass of the string, but I need to know what is mu first. So v squared is F0 over mu. So mu is F0 over v squared, right? So from here, F0 is the tension, which I calculated to be mg, and v squared is the speed. So what is the mass per length? We are given the mass. The mass is 54 kg, so put 54 here. Gravitational acceleration is 9.8, and then the speed, well, the speed, right, just now according to what we said, that given the time taken is 0.0942 to travel from bottom to the top. So given the information, we can calculate the speed to be the length over the time, right? So the length is 3.80, and then the time is 0.0492 seconds. So the speed shall be 77.24 meters per second. So I can use this to determine this. So I got the speed now. I put this in here, 77.24 square. So my mass per length is 0.0887 kg per meters. So this is the mass per length. So the total mass of the string right? So I'll call this big M because I already call this small m, right? So it's equals to mass per length times total length, right? So it's equals to mass per length is 0.0887, and the total length was 3.8 meters. So the answer is 0.337 kg. Right, so this is how you get the system. Okay, so that was some question 3. Okay, so question 4 is about some standing waves. So let me remind you a few facts about standing wave. Okay. So for standing wave, right, I have, so I can have a wave vibrating a string with fixed endpoints, right? And then the possible wavelength on the string is, if the distance is L, is usually fixed like on the guitar, right? The possible wavelength on the wave is 2L over N, and the possible frequency is given by N over 2L, and then the F over mu 0. Right, so these two are related because V is equals to F times lambda, and also V is equals to F0 over mu. Okay, so all these equations are related from, we can get this from the relations of the standing wave. Okay, so what is question 4 about? So question 4 is, I got a 1.5 meter rope stretched between two supports with a tension that makes the speed traveling this much. What is the wavelength for N1, N3, and N4, right? So this one is also very simple, right? So it seems like when it comes to wave, as long as you understand the concept, it's very straightforward. Okay, So for question 4, the L is 1.50 meters. The speed of the wave is 4 meters per second. Right? From there, we can calculate the various frequencies. Okay, so for example, right? For example, n equals to 1. For n equals to 1, I put this n equals to 1, so the wavelength is 2L. Right? So if I put this 2L, then if I times 2, I get 3 meters. Then how do I get the frequency? So the frequency, I can use V is equal to F lambda. So the frequency is just the speed divided by lambda. So the speed is 48, the lambda is 3. So the answer is 16 hertz. Right? So I got this. And then if I do n equals to 2, no, I want 3. Right? So lambda is going to be 2L over 3. So lambda is 2L over 3. And then, so this is going to be equals to 2, 1.5, and 3. So it's 0.7, no, it's just 1 meters. Right? And then the frequency is just 48 over the wavelength, so it's just 48 hertz. Right? So how about n equals to 4? When n equals to 4, I just put in 4 here, so it's just L half. So it's 2L over 4, so it's just L over 2. So it's 0.75 meters. Right? And then the frequency is just 48 over the wavelength that you gotten. 0.75 is 64 hertz. Okay, so these are the answers that you can get pretty straightforwardly. Okay, so far so good, right? Yeah, pretty straightforward for all these questions. Maybe slightly less straightforward is question 5. Okay. What's question 5 about? So I have a wire. The mass is 40 grams, stretched and ties down at points 80 cm apart. So the length is given here, 80 cm. So might as well write it down. The mass is 40 grams. So I can easily convert to kg later, and then the length is 80 cm, right? And then the fundamental frequency is 60 hertz, and the amplitude. So I didn't teach you what is antinodes. So don't. This one is from the textbook. So never mind. It doesn't make a difference to us. We just need to know the amplitude is 0.3 cm. Okay. So what is the speed? What is the tension and the maximum transverse velocity of the wire? Wait. Sorry. Okay. So yeah. So fundamental mode is the lowest n. So n equals to 1. So fundamental mode. So when you see fundamental mode, right, it means n equals to 1, right? So when n equals to 1, I can plug in n equals to 1 to all these formulas. Where's the formulas? So n equals to 1, I can get lambda, I can get f, I can get all this information from here, right? So pretty straightforward. So the lambda is 2L, right? And then from this, I can get the v is equal to f lambda. So this is 2, it's just f times 2L. So the frequency is just 60 times 2 times the L is 80 cm, so it's 0.8 meters. So it's 96.0 meters per second. So this is the speed of the wave propagating in between the two. Hungry, ah? Actually, I'm hungry too. I haven't eaten anything today. Yeah. So, yeah. So let's finish at 12 and then lunchtime. Okay. So the next thing is, what was the next thing? I want to know what is the tension of the wire. So I shall be using the formula since I know the speed already. So I use this to get the tension. So the tension is just solving for F0. So F0, I square both sides, is just V squared mu, right? And then what is mu? So mu is not given, but you're given the total mass of the wire and the total length. So it's just the total mass or total length. So the V, so we can easily calculate this as well. So the V is 96. Total mass is 40 grams. So it's 0.04 kg. And then the length of the wire is 0.8 meters. So I can calculate the tension after putting everything is 460.8 newtons. Okay, and then now this next part is slightly more tricky. What is the maximum transverse velocity and acceleration of the particles on the wire? So now I'm talking about the transverse direction, not the propagation direction. This is a transverse wave. So I need to use my wave equation now. So I got A. According to, this is a standing wave, right? So the standing wave, we have solved this already. So the result is A sine kx cos omega t, right? This is the standing wave solution. We have solved this last week, right? And then I want to calculate my velocity. So my velocity in the y direction is, I differentiate my y with respect to t, right? So partial derivatives. Okay, so this is the velocity for y. So if I differentiate y with respect to t, I got negative omega a sine kx. Differentiate this sine omega t. Okay, so I want to know what's my maximum, right? So maximum is when these two functions could be 1. So my maximum velocity is just equals to, well, the maximum corresponds to 1, so it will be omega times a, right? So what is omega times a? Omega is 2 pi f, and then the amplitude. So the frequency is given, the amplitude is given. So I can calculate everything to be 1.13 meters per second. Okay, so that is my maximum transverse velocity. How about my maximum transverse acceleration? I need to differentiate this a second time, right? So my maximum transverse acceleration is partial y partial t squared. That means I differentiate this with respect to time again. So differentiate this, the omega comes out. Sine kx is unchanged. Differentiate sine becomes a cosine. Okay, so this one, if maximum, this is equals to plus minus 1. So corresponds to my maximum transverse acceleration is just equals to omega square a. So it's just 2 pi f squared times a. And f and a are given. So square this times this, you get 426 meters per second squared. Why is it such a big number? Correct or not? Yeah, so it's 60 square, right? Let me check. So 2 pi times 60, the answer square, and then times 0.3 times 10 to the minus 2. Yeah, 426. So it is, the acceleration is quite large for this system. Kind of makes sense, right? Because the tension is large, so the order of magnitude of the forces is around the same. Because the order of magnitude of mass is 40 grams, so it's not very big or not very small. Is it? Huh? So they steal things in the fridge, so terrible. Well, I need to lose weight lah, so I need to eat less carbs. Yeah. So usually my habit now is only lunch and dinner. I got used to not eating breakfast. Yeah, because if I eat breakfast, then I gain even more weight. So more sports. Don't dinner. Is it? I can try that, but if I skip breakfast, I feel less hungry. Yeah, then I can survive if I skip dinner, is very difficult for me. So let's go to, what time is it now? Yeah, we got plenty of time. So let's do one more question from here. Let's do question 6. And then I discuss an interesting question about oscillation. So we have a piano wire. The mass is 3 grams. The length is 80 cm, stretched with a tension of 25 newtons. Wave with frequency 120 hertz, and this amplitude travels along the wire. I want to calculate the average power. So this one is pretty straightforward also. So actually, yeah, the derivation is like a lot of very scary mathematical things, right? But those are the derivation part, which you don't need to worry about. The actual solving question is for wave problem is very simple. But yeah, except for the double slit and the Doppler effect, which we haven't discussed yet. So the mass of the thing is 3 grams, right? The length is 80 cm. So from here I can already calculate the mass per length. So it's I prefer to convert to kg. So this is this kg and this many meters. So this is 3.75 times 10 to the minus 3 kg per meters. And you're also given that the frequency of this thing is 120 hertz and the amplitude is 1.60 millimeter. So millimeter is 10 to the minus 3, right? And calculate the average power. So the average power, the formula that we have derived last time is mu v omega square a square. So just plug in all the values, right? So the only thing that we don't know is the v. Now the v is just the frequency over the the tension over the mass per length. So I got this now, and omega square a square. So if I put this in, so I got half mu f0 omega square a square. So now I have all the numbers, so I can compute the final answer to be 0.223 watts. Okay, so this is just calculating the average power on the system, right? So the information not given is V, but I can determine the V using this information. Okay, so it's still possible to get the answer like this. And then for the second part, right? The second part is also very simple, because if the amplitude is half, what happens to my average power? So my original formula was half mu v omega square a square, right? And if I have a new amplitude that is half of the original amplitude, then what happens to my new average power? So my new average power is half mu v omega square, half of my original amplitude. So half square is 1/4. Then the rest is just half mu v omega square a square. So this is my previous power. Okay, so my new power transfer is a quarter of my solution that I got just now. So my previous solution was 0.223 watts, so it's 0.056 watts. Okay, so that is the solution that I got by just using the power formula. I think you mean muscle, right? I assume you mean muscle, just the typo error. Yeah. Oh yeah, I'm not in school. Yeah, I'm in my house. Yeah, can consider lah. Yeah, so I'm already like my food is already like super healthy. I cook myself, very few oil. Sometimes I buy fruits, but mostly I cook a lot of veggie. Very few rice and very few meat. Okay, so actually we can start talking about Doppler effect. We have about 20 minutes left. So let me discuss one thing. Yes, I do need exercise. So occasionally I would exercise sometimes. So I will use some remaining time to discuss about something that I sort of ignore in chapter 8, because chapter 8 I sort of like focus on the simple case. But right now, right, let me consider this because this one, someone asked me this, so I thought it would be interesting to cover. I want to talk about a spring with an external force, constant external force. So how do I solve the spring with a constant external force? Okay, so a common situation is like I have a vertical spring. Okay, so I want to prove to you, right, that even with a constant external force, the frequency of oscillation is the same, right? The frequency will be the same, just that the position will be slightly different from the original situation. Because original situation, right, originally I have a horizontal spring. So horizontal spring, there's only one force acting on this object, the spring force, the Hooke's constant, the Hooke's law, right? But if I have a vertical spring, then I got the gravity now. So how do I solve this? Okay, so let me draw this situation. Let's say this is my x-axis. I have a spring suspended from a ceiling. Okay, so I have a spring suspended from a ceiling like this, right? And then this is my, let's say my natural length of the spring is here. Okay, so natural length is some fixed constant of a spring, but if I suspend it vertically, right, will the mass be located at the natural length? No, right? Because there's a gravity, so it's going to pull it down a little bit, right? If you put it horizontally, the natural length will be L, but if you put it vertically, the weight of the mass will be a bit lower. Okay, so let me put my coordinate system as this. So this is my origin. Okay, so my natural length is located at 0, but in a vertical, right, it's going to stretch down a little bit, so my spring is going to be somewhere here. Okay, so and then this is, let's say this is before oscillation. So if before oscillation, right, the position of my spring is the equilibrium position. Okay, so this is my equilibrium position. Okay, so my spring is here. Okay, so what are the forces acting on the spring? So the forces acting on the spring is the weight, right? So so the net force acting on the spring is using Newton's law. So the net force acting on the spring is equals to mass times acceleration. This is the mass of the block here. What is the net force? So there is a weight coming down, right? Up is positive, and then there is a spring force. So the spring force is always negative from your equilibrium position, so it's negative kx. All right, and then my acceleration is dx dt. Okay, so do you agree with this situation so far? Oh, yeah, so tutorial exercise is a form of exercise, right? You divert all your calories to your brain consumption rather than your body. Okay, so everyone agree with this equation, right? So this one is not yet oscillation, right? Not yet oscillation. Firstly, let me hang the spring vertically first, right? So if I hang the spring, what is the equilibrium position? How far below the natural length of the spring? So let us calculate the equilibrium position. By the way, yeah, so this is the situation where this is a simple harmonic oscillation, but I have a constant external force. Okay, but first let us find the equilibrium position. Okay, so my equilibrium position, well, I want this to be net force to be 0. So negative mg minus kx to be 0. So x is equal to negative mg over k. So this is my equilibrium position, right? So this is equal to negative mg over k. So this is, yeah, that's why it's negative, right? It's below 0. So this is my equilibrium position. Okay. Yeah. So now now we start to do oscillation, right? So I have a hanging spring, right? So it's going to be slightly longer than the natural length, and then if I disturb the spring a little bit, it will start to vibrate, right? It will start to vibrate. What is the frequency of oscillation? So this is what happens when the spring is disturbed. Okay, so it will oscillate about the equilibrium position. Okay, so it oscillates about the equilibrium position. In other words, it does not oscillate about the natural length. Okay, so because my spring is here, and then if I disturb the spring a bit, right, it will start to do some oscillation, right? So it will start to oscillate up and down, right? So it will start to oscillate up and down, and then yeah, it's going to be the amplitude of oscillation, right? So oscillate. So how do I solve this motion? Okay, so let me say, right, so in order to solve this differential equation, it will be easy if I define a new variable. So I'm going to define a new variable. I'm going to let's call this new variable u. Define u to be the displacement from the equilibrium position. So in other words, u is defined to be x plus mg over k. Okay, so this new variable, right? So let's say my box is here, then this distance is u is equals to x plus mg over k. Okay, so does it make sense? It makes sense, right? Because when x is negative mg over k, u is 0 displacement from the equilibrium, right? If x is higher, I get a positive u. If x is lower, I get a negative u. Right? Makes sense, right? So u is the displacement from equilibrium. So in other words, I got x is equals to u minus mg over k, right? So now I'm changing my variable. So I'm going to substitute this into equation 1. Right? So if I put this into equation 1, let's see what happens, right? So if I substitute this into equation 1, right? So what's my equation 1? So my equation 1 is minus mg minus k times x. So the x is, I substitute here. So x is u minus mg over k. And then this is m. And then this is dx dt. Right? So this is dx dt. Like this. Over here. Oh yeah, so x is also substituted. I forgot. So this is u minus mg over k. So minus mg minus k u minus mg over k, and then m second derivative u minus mg over k, right? So let's expand and simplify this equation. So I got ku plus k times mg over k, and then on the right hand side I'm differentiating u minus a constant. So this is a constant, so if I differentiate the constant, it will disappear. So I have m d2u dt squared. Okay, the k and k will cancel, and then this is positive mg cancel with negative mg. So I got negative ku is equals to m d2u dt squared, right? So in other words, the second derivative is equals to negative k over m times u. So this is a simple harmonic equation for u. So the solution is, we have given this differential equation. I have shown you on chapter 8 how to solve. It is a sine omega t, right? So sine omega, or I use cos, right? So omega is this omega is given by this coefficient, and it is the same as the same formula as just now, so it's KOM. Okay, so finally I got the this is my displacement, so I need to express this back in terms of x. So my x is equals to ut minus mg over k. So my solution is this thing minus a constant. So it is just the same situation, but I have a constant at the back. Okay, so this will describe the oscillation of a vertical spring. Right, even if there's a constant external force, the frequency of oscillation is the same, right? The formula is for the displacement from equilibrium. So to get back your original, you just do this. Okay, so yeah, so one of you guys, I don't want to reveal the name yet, but someone asked me this question, how to solve the vertical spring. So hopefully this makes sense to you. Okay, so this is the simple harmonic oscillation. Okay. So does anybody have any question? Yeah, so if no question, then since we still have time, yeah, how come I have so much time today? That's very unusual, right? So let's continue on with Doppler effect. 8, 9, 10. So this is page 11. Yeah, so let's start a bit about Doppler effect, and then we continue the rest on Wednesday once we run out of time. So actually it's about 6 minutes left. So let's talk about the Doppler effect. So this time, so just now for double slit is interference of light. Now I'm talking about Doppler effect where my wave now is sound. So this one is, I want to study the case where the sound is the special case where sound is the longitudinal wave. Okay, so remember that wave is the disturbance of a medium, right? The medium is air. Okay, so yeah, so right now people can hear sound, we can talk to each other, we can detect sound, is because we are surrounded by air. So when we talk, right, we disturb the air molecules and the disturbance will propagate, and then our ears will detect them as the sound, and this is how we hear things. Okay, so the medium is air, so we measure the disturbance of the medium right, by how the air pressure changes, because when there's a disturbance, right, the air pressure will change slightly because of the disturbance. It will increase and decrease about the equilibrium. So it will change by variations of the air pressure. So we calculate the pressure at time t and at position x to be some amplitude of pressure, right? So this is the pressure at equilibrium, and then sine kx minus omega t. Okay, so this is the formula, but we again, right, this is we do not really care about the details of how the sound waves are generated, because these are like for later course. We just need to study the phenomena of waves itself. Okay, so we just need some few basic facts. For example, right, the speed of sound in dry air at 20 Celsius is equals to 343 meters per second. So it changes depending on the temperature and the humidity and the basic properties of the air, right, or the ionization of the air. So it varies. Okay, so that is the information that we will probably need. Don't need to memorize, it will be given depending on the situation. Okay, because for different temperature you get different velocity, so we can't memorize all the situations. Okay, so what is the Doppler effect about? So the Doppler effect, right? The Doppler effect happens when a source emits the sound, right? There's going to be a sound that is generated at some frequency and at some wavelength, right? So because of this, the wavelength and frequency will be related as usual by V is equals to F lambda. So we probably experience this in everyday life, right? If we stand beside the road and then we see a car coming by, so you hear the sound like the race car. The sound, the frequency of the sound changes, like the race car, the sound is like the that kind of sound, right? So you know what I'm talking about, I hope. If a car press the horn, right, the horn also, when the car is approaching, the sound increases, and then if it goes behind us, the pitch and the tone decreases the sound, right? So that is the Doppler effect. Okay, yeah, great. So the kx is because equation 1, yeah, correct, is away from the natural length of the spring. Yeah, you mean the spring thing, right? Yeah, so it's just the x-axis coordinate and then x equals to 0. So the equilibrium position is over here, and we solve using the usual Newton's law. The direction of vibration is same as object towards. Yeah, for sound, yes. Yeah, for sound is the longitudinal waves. Okay, so let us see how far we can go before we run out of time and everybody is hungry apparently. So let's consider a case of a moving observer. So we studied the complete cases, everything on Wednesday, but now let's look at moving observer and a stationary source. Okay, so I'm about to draw an ugly picture. The nicer picture is in the lecture notes. So I have a source here, right, is emitting a sound. So the sound has a wavelength of lambda, right, and then the observer is moving at the speed of V observer, so VO. Okay, so the situation is like this in the lecture notes. Yeah, so this picture. Okay, so what I have here is a source emits sound at frequency. The original frequency of the source will be Fs, right? So that's the original frequency of the sound, and then the wavelength generated will be depending on the speed of the wave in the air, right? So the wavelength generated is using the formula is Vf lambda. So V is the speed of sound in the air, so the wavelength generator is just V over frequency Fs. Okay, so given this situation, what is the measurement of the observer? So the observer measures so the wavelength is like this, right? So so the speed of the wave, the incoming wave of the observer, is going to be the relative velocity. So now, because right, this is relative velocity problem. So if the speed of sound in the air is just V, but if the observer is running towards the sound, then the speed of the wave as measured by the observer is V plus V0, right? It's even faster. Okay, so that means the frequency observed, okay, so it's going to be equals to V plus V0 equals to F lambda. So this is the frequency that was observed, and the lambda formula was from here, so we put this in, right? And then what we have here is just f0 v over fs. So the frequency observed is just going to be solving for f observed, then fs I bring over, I got v plus v0 over v fs. So the frequency that the observer hears is different from the frequency that the source hears, and it's because of this formula. And the reason is because the observer is running into the sound. If you're running into the sound, right, the amplitude and minimum, the oscillation, the frequency is higher, right? Because from the perspective of the observer, the changes from maximum to minimum occurs at a faster rate because you're running into the sound. So that is the first formula of Doppler effect that we are learning now. Okay. So now it's just time. Yeah, good time for hungry people to eat lunch now. So I guess we can stop the class for today, and we continue the rest on Wednesday. And also Wednesday we will have our quiz. So don't forget to do the quiz as well.